Hello, welcome to Equity Education, the chemistry version, and today we're going to be looking at some more organic chemistry and specifically haloalkanes. Okay, not quite as much as we usually cover with our organic chemistry, so hopefully you can get through this in one sitting. Okay, so I need to open your booklet and we'll get started. Okay, so haloalkanes, first thing is that you may see different names for haloalkanes. So, may be described as haloalkanes, haloalkanes, which is the notation that I will be using, and alkyl halides. Okay, so just to let you know, they're all the same. Okay, so all the same. Okay, my general formula for a haloalkane is CnH2n plus 1 and X. Okay, and X stands for any of my halogens, so could be F, C, Br, or I. So it's a halogen atom attached to carbon and hydrogen chain, so an alkyl chain. Okay, so moving on. So naming and classifying. Alright, so I'm going to draw some. Let's have a go at drawing them, and you can have a go at naming them, and then we'll classify them. Okay, so if you can draw these. And I'm just going to change one of them because that should be CH3. Okay, I'd like to have a go at naming these. Okay, I'll give you a minute. Okay, I'm sure you've all managed to do this. So, as always, when we're naming organic molecules, we count the longest carbon chain, so 1, 2, 3, so it's prop, and we put the halogen atom at the start, so in this example it would be chloro, so chloropropane. Middle one, 1, 2, 3, is our longest carbon chain, which means the chloro is on the second carbon, so 2 chloropropane, and on the third one, 1, 2, 3, is my longest carbon chain. So 2-methyl, 2-chloropropane. And in fact, obviously we could write that slightly better because really we should have our chloro first. So 2-chloro, methyl propane. Okay, so classifying. So if you've looked at the alcohols video, we know that we classify alcohols by looking at the COH bond and looking to see how many carbons are attached to it. Exactly the same for classifying my exactly the same for classifying my haloalkanes as well. So when we're classifying, we look at the CCl bond and count how many carbons are attached to the C in this bond. So in our first example, we look at this carbon, we have 1 carbon attached, so it will be primary. This we have 2, so secondary. Here, 1, 2, 3, so tertiary. We classify them exactly the same as alcohol, so primary, secondary, or tertiary. Okay, so moving on. So physical properties. So haloalkanes are simple molecular structures with permanent dipole to dipole. So to write down here, interactions, and also London forces. So because they're simple molecular structures, we're talking about the intermolecular forces when we're talking about the boiling point or some of the physical properties. And they have permanent dipole to dipole interactions. That's because there's a difference in electronegativity between my carbon, I'll show you here, my carbon and my halogen atom. So the halogen atom is more electronegative, so this will become slightly positive, slightly negative, this will become slightly positive. Hence my permanent dipole-dipole interactions. And we also have London forces, because every single molecule will have London forces, every single simple molecular molecule. Okay, so in general, therefore they have, low, you may see it described as medium, but generally they're low boiling points. Okay, so chloromethane is a gas at room temperature. Iodomethane is a liquid at room temperature. Okay, and we know that the CCl bond is more polar than the Ci bond. Okay, so that must mean that this indicates that the polarity, so the strength of the carbon-halogen bond, is not the major factor in boiling point. The polarity of the C-Hal bond, so the polarity of the C-Hal bond decreases down the group. Again, I'm not going to go into too much detail here. You can have a look at simple molecular structures for this. Rather, it is the increase in London forces down the group because the halogen atom gets bigger, therefore there are more electrons, and therefore an increase in London forces between the molecules. Okay, so as this halogen atom gets bigger, that means that we will have more London forces, and therefore there will be stronger for intermolecular forces, so it requires more energy to overcome. Exactly the same reason as why boiling points increase with carbon chain length with alkanes as well. So if we have a longer carbon chain length of haloalkanes, we're increasing the number of electrons, we're increasing the surface contact, we're increasing the intermolecular forces, therefore we will increase the boiling and melting points. Okay, so moving on. So they are slightly soluble in water, and the reason why they are only slightly soluble in water is because they cannot form hydrogen bonds with water, because we don't have a nitrogen, oxygen or fluorine attached to a hydrogen in our haloalkanes, directly attached. Okay, and we'll just write here that this means they are usually dissolved. We'll write this again later, in ethanol, which is our solvent in reactions. Not always, but mostly. Okay, and we'll talk about that in a little bit. Okay, so reactions. Don't know why that's all the way down here. So in reactions, which is basically what we just said, so in reactions the haloalkane needs to be dissolved in ethanol. Then ethanol is used as a solvent to make the haloalkane. and water mix. Because they're not very, they don't dissolve or mix very well with water, we use the ethanol, and that makes the water and the haloalkane mix a bit better. Okay, so we can provide these hydrogen bonds. Okay, so hydrolysis reaction. So how can we describe a hydrolysis reaction? So a hydrolysis reaction is a reaction where water or hydroxide ions are used to break a bond. In a reaction. Okay, and you need to know about hydrolysis reactions. Okay, so the general formula for hydrolysis reaction is my haloalkane plus OH minus. You may also see it with water. We'll do another example of water in a bit. Goes to an alcohol plus X minus. And we'll do a specific example, e.g. so we'll have chloropropane plus OH minus goes to propanol plus my halide ion. Okay, so my haloalkane, chloropropane, forms propanol. Okay, so what do we need for this reaction to happen? So we need to heat under reflux, and also we need to use ethanol as a solvent. Now I've added hydroxide ions. You could just add water, and we'll do an example of that in a little bit. Okay, sorry. So water on its own can be used, but adding an alkali makes the reaction much quicker. So we'll just do an example using water. Let's do it with Br this time, plus H2O would form, again, my alcohol. But I'm only under the OH here, so I have one hydrogen left, so I'd form HBr. So water on its own can be used, as I just said, but adding an alkali makes the reaction much quicker. Okay, so moving on to reaction mechanisms. Okay, so what does the reaction mechanism look like? So we start with our haloalkane. We'll do chloropropane. So it looks like this. So we'll do this reaction. Now, because chlorine is more electronegative than carbon, I'm going to have a dipole set up here. Yeah, so there's going to be a polar bond. Now, my nucleophile is my OH. Okay, my hydroxide ion. Now this lone pair is attracted to my electron deficient carbon atom, my positive carbon atom, and it forms a dative covalent bond. That means this covalent bond breaks, and I'll just show it a bit clearer. So this covalent bond breaks. We form a new dative covalent bond with the hydroxide, with the OH minus, and we remove our halide ion. So there's two different mechanisms that are involved in haloalkanes. I'm only going to do this one. Okay, so what do we call this? Well, this is a nucleophile. So we call this nucleophilic, and if you look, what's happened? we have substituted in the hydroxide and removed the chloride ion. So we call this nucleophilic substitution. Okay, if we were going to describe this, we would say the alone pair on the hydroxide ion, it's a lone pair of electrons, is attracted to the delta positive carbon atom. Dative covalent bonds here, dative covalent bond forms, and we called this is known as nucleophilic attack. The covalent bond between the C halogen, so this is my C halogen, breaks to form a negatively charged halide ion, as we've shown up here. This is via heterolytic fission, because both the atoms, both the electrons from the covalent bond go onto one atom, and we form this negative ion here. Okay, another definition, because I don't know if we've defined this yet, so nucleophile. So nucleophiles donate a pair of electrons. That means we need usually a lone pair, and it's usually charged as negative. So they're attracted to an area which is positively charged, so an electron deficient area, and this lone pair of electrons can then form a dative covalent bond. Okay, so moving on. Rates of hydrolysis. Okay, so as you go down group 7, the rate at which haloalkanes hydrolyze, they increases. And when we're talking about hydrolyze, what we mean is this reaction here. Yeah. So the reaction mechanism is nucleophilic substitution, and we call it a hydrolysis reaction. So we're still forming this alcohol. Okay, this is because the enthalpy of the C-Hal bond decreases as you go down the group. Now when we're talking about bond enthalpy, it's the energy required to break 1 mole of gaseous covalent bonds. Yeah, so the energy required to break this bond. Okay, and we can fill this in. So CFCCl CBrCl plus 467 plus 340 plus 280 plus 240. Okay, so this means that it requires less energy to break the carbon halogen bond as we go down the group, and because it requires less energy, the rate of hydrolysis, or the rate of reaction, increases. Okay, so what does that mean? So this means the rate of hydrolysis is dependent on bond enthalpy, or the strength of the carbon halogen bonds. Okay, so we can show this through experimental observations. Okay, so how do we do that? So how we do it is to 3 separate test tubes, add chlorobutane, bromobutane and iodobutane, add aqueous silver nitrate and ethanol, and we observe when a PPT, a precipitate, is formed in each test tube. So what's happening? So the ethanol, what's happening in the reaction? So ethanol acts as a solvent, the water acts as the nucleophile. Now you might say, where is the water from? So we haven't added anything. It's because we've got aqueous silver nitrate here. So here is our water, okay? And the silver nitrate, I will write the chemical equation. So you've got both versions. So AgNO3 reacts with the halide ion to form the precipitate. So the precipitate is the observable reaction. Okay, so what's actually happening in this reaction above? So, well, first thing is that we're adding water and ethanol used as a solvent to our haloalkane. So we get a hydrolysis reaction. So firstly, what have we used? So we'll use bromobutane as the example. So CH3. Actually, I would like you to have a go at writing this first reaction. So what happens when bromobutane is added to water and ethanol? Okay, I'm sure you've all worked this out. So this is a hydrolysis reaction, and we're taking a haloalkane reacting with the water, breaking a bond using water to form an alcohol plus HBr. And I've separated the HBr just because in our next step we're going to use this Br minus. You might see HBr aqueous written together. Okay, so we also have aqueous silver nitrate in there. So we know that if we add silver nitrate, we get the halide test. So our silver will react, our silver ions will react with my bromide ions, and it will form AgBr, which is a solid, which you probably know is a cream precipitate. We know it's a solid because we have a solid state symbol here. Okay, so this is our observable reaction. Okay, so if we're doing this test to determine the rate of hydrolysis, we add aqueous silver nitrate and ethanol to 3 separate test tubes, and we see which precipitate forms first. Now we've said that the rate of hydrolysis increases down the group, therefore we will see our iodobutane precipitate form first, then bromobutane, then chlorobutane, because iodobutane has the lowest bond enthalpy between the carbon and carbon and halogen. Okay, moving on. So again, just to make this point very clear, rate of reaction in haloalkanes, especially when we're talking about hydrolysis reactions, just put it in brackets, is not to do with polarity, it's to do with bond enthalpy. Right, so if you're going to perform this test, you need to keep the test fair, so you would use equal amounts of the haloalkane, use haloalkanes with the same carbon chain length, and use a water bath to keep a constant temperature. Pretty self-explanatory. Okay, so we're just going to go through some uses of haloalkanes, and these are things that you've just got to remember. Okay, so haloalkanes are used to make different types of plastics or polymers. CFCs stand for chlorofluorocarbons, used to be used in refrigerators and aerosol cans. However, they damage the ozone layer, therefore their use has stopped, and their use has stopped from the Montreal Protocol Act. Okay, ozone layer. So the ozone layer stops harmful UV radiation reaching Earth. Excess amounts of UV radiation can cause sunburn and mainly skin cancer, but lots of different types of cancer. Ozone. Looks like O3. And you can actually smell ozone. And ozone exists in equilibrium as shown above. So O2 plus O forms O3. Okay. At high altitude, oxygen molecules through break through photodissociation by UV light. So photodissociation, we'll just define that, means breaking a bond via UV light. Okay, so my oxygen molecule would break, the covalent bond would break to form two free radicals. Okay, and an oxygen free radical reacts with an oxygen molecule to produce ozone. So this is how our equilibrium is set up using these reactions. If I added them up, so O2 plus O goes to O3. Okay, so now actually the holes in the ozone layer are starting to heal, but it still is a problem. So holes in the ozone layer. The ozone layer has been thinning because ozone can react with chlorine-free radicals and can react with chlorine-free radicals from CFCs and nitrogen-free radicals from thunderstorms. So chlorine-free radicals, how do they react? So this is a free radical substitution reaction. So my overall equation would be O3 plus O goes to 2O2. So the chlorine-free radicals, they break, we'll write it down here. So first of all, we'll do our initiation reaction. So I have my CFCs. So different types, but I'm going to use CF2Cl2. I add UV light to produce two free radicals. And usually the carbon Cl bond breaks first. If you probably remember why, because it has a lower bond enthalpy than CF. Okay, so we have formed two free radicals via homolytic fission of this CFC. Now the propagation reactions, again, you just need to remember. So I take my chlorine free radical, it reacts with the ozone to produce oxygen and another free radical. My next free radical can react with oxygen to produce O2, and my chlorine free radical, and then maybe another step is that I can take the ClO free radical and react it with O3, and again produce a chlorine free radical. You may notice that the chlorine free radical is at the start and the beginning of all these steps, so the chlorine free radical can be considered a catalyst. Okay, nitrogen free radicals. So how do we get these nitrogen free radicals? So nitrogen free radicals are produced at very high temperatures in jet engines, so planes, and thunderstorms. Okay, and we only need to do the propagation step, so it's very similar to our chlorine free radical. O3 goes to NO2 plus O2, and then NO2 plus plus O goes to NO plus O2. And again, the nitrogen free radical can be considered a catalyst because it's at the end and the beginning. Okay, so for some reason these CFCs and these free radical substitution reactions are in a lot of syllabuses. You don't need to know how they particularly work, but you just need to remember the equation. So I'm not going to go through in any more detail. If you're unsure about free radical substitution and how it works, go back and look at the free radical substitution video, which talks about alkanes and halogens. It's much more self-explanatory. Okay, right, so we've got a couple of questions to do. I'll give you about 10 minutes and then we'll go through the answers. Okay, we'll go through these questions. So 2-bromopropane reacts with an alkeous alkali. Write the overall chemical reaction equation. So this is a hydrolysis equation, and we're going to produce a secondary alcohol, so propan 2-ol, by removing my bromide, my halide ion. Describe the mechanism, state what type of reaction is occurring. So I've shown you the important things you need to include using the red arrows, so my dipoles, forming the dative covalent bond with the hydroxide ion, and then breaking the CBr bond, covalent bond, via heterolytic fission. And we call this nucleophilic substitution. Okay. Describe a test that can be carried out to determine the rate of hydrolysis of the haloalkanes down group 7 using 2-bromopropane as one of your reagents. So we would add aqueous silver nitrate and ethanol to 3 separate test tubes of 2-chloropropane, 2-bromopropane and 2-iodopropane. See that they're all propane, so we're keeping the carbon chain length the same, otherwise it wouldn't be a fair test. Time how long it takes for a precipitate to appear. This will tell us the rate of hydrolysis. And make sure equal amounts of haloalkane are used and keep temperature in each of the reactions constant. Okay, so not as long as usual, so that's probably good. Hope you managed to get through it. And as always, I hope that was useful, and I will see you next time. Okay, bye bye.